So good afternoon, this is Min, and today I'm going to introduce you our work, Inference Attacks Against Graph Neural Networks. This is a joint work from CISPA and Norton. First, I will give you some examples of graph data. Many real-world systems consist of nodes and edges, and thus can be represented as graphs. For example, the social network, financial network, and chemical network. Two of the most important tasks of analyzing graph data are node classification and graph classification. The objective of node classification is to determine the label of each node in the graph, and the objective of the graph classification is to determine the label of the whole graph. And the most straightforward method for the node classification is just ignore the edges and directly feed the node features into an MLP model. And this model can predict the label for the nodes. However, this method, ignore the edge information, cannot explore the information from the neighboring nodes, which has shown is important for node classification. So here comes the graph neural networks, which is also called GNNs. The general idea of GNN is to aggregate the information from the neighboring nodes and generate node embeddings for each node. The node embeddings can then be used to conduct some downstream tasks. For example, the node classification or link prediction. The most important component of GNN is the message passing. So there are multiple algorithms for aggregating the information from neighboring nodes. For example, the graph convolution neural network, the graph isomorphism neural network, and the graph attention network. And the node embeddings we got can further be summarized as graph embedding for some graph classification or graph matching tasks. And this process is called graph pooling. And there are mainly two categories of graph pooling method, the global pooling and hierarchical pooling. So the global pooling is quite easy. Just directly summarize all node embeddings to a single graph embedding vector, such as take the average or take the maximum. And here is a pipeline of generating the graph embedding in a hierarchical way. First, we use message passing modules to obtain the node embeddings, and then we find multiple clusters according to the node embeddings we found. And next, we treat each cluster as a node, and node feature here becomes to the graph embedding of that cluster. Then we iteratively applying the message passing and the clustering operations until there is only one graph embedding. So in this paper, we focus on the whole graph embedding, which is usually computed on sensitive graph. And such graph embedding is empirically considered centralized since the whole graph is comprised into a single vector. In practice, it has been shared with the third parties to conduct some downstream tasks. For example, the graph classification, graph matching, or the graph visualization. Our threat model here is that when an adversary can access to a graph embedding, the information of the original graph that used to generate a graph embedding can be leaked. Specifically, we conduct 3 inference attacks: the property inference attack, the subgraph inference attack, and a graph reconstruction attack. I will introduce them one by one. So the first one, graph property inference attack. An attack objective is that given the tagged graph embedding, infer the basic properties of the tagged graph, such as the graph density, number of nodes, and number of edges. To achieve this goal, we use a multi-output classifier as the attack model. The attack model consists of a feature extractor and multiple output layers. Each output layer predicts one graph property. So to train this Attac model, we can use a set of auxiliary graphs that comes from either the same or different distributions as a Attac graph. And here is the Attac performance. We evaluate on 5 datasets and 3 properties. So we'll first bucketize each property into 4 different bins. We consider 2 baselines in our experiment. The first one is quite easy, just a random guessing. The second one is directly summarize the properties from the auxiliary dataset. We also consider 3 pooling methods. Min pool is a global pooling method. Diff pool and the min cut pool are the hierarchical ones. By comparing the first 3 and the last 2 bars, we show that our proposed Attac consistently outperformed baseline. Yeah, here's the first conclusion. And second, we observe that larger bucketization can lead to worse performance. This is expected because larger bucketization requires higher granularity of the graph structure information and is more difficult for the classifier to distinguish. In addition, we found that Attac performance on min pool is worse than the other 2. And this is because that min pool directly average all the nodes from the embedding into a whole graph embedding, which might lose some graph structure information. Okay, so here is the second Attac, subgraph inference Attac. The objective here is that given the tagged graph embedding and a subgraph of interest, the attacker aims to infer whether the subgraph of interest is contained in the tagged graph. Since the tagged graph embedding and the subgraph of interest are in different formats, we cannot directly compare them. To address this issue, we first use an embedding extractor to transform the subgraph of interest into subgraph embedding. Then we merge the tagged graph embedding and the subgraph embedding and feed them into an MLP model. The MLP model can tell whether the subgraph of interest is contained in the tagged graph or not. The whole Attac model consists of the embedding extractor and the MLP model, and they are trained together on a local auxiliary dataset. To train the Attac model, we need both positive pair and negative pair. The positive pair means the subgraph is in the tagged model, and negative pair means the subgraph is not contained in the tagged graph. And to generate the positive pair, we use graph sampling methods such as random walk to generate a subgraph from the tagged graph. To generate the negative pair, we randomly sample a graph from the auxiliary dataset that is different from the tagged graph. And we sample a subgraph from this graph. The tagged graph and the sample subgraph together to be the negative pair. And here is the result of the subgraph inference Attac. We consider 4 different sampling ratios, which indicates the proportion of the subgraph in the tagged graph. Here, yeah. To conduct the subgraph inference Attac, the most straightforward method is to generate the subgraph embedding directly using the tagged model and only train the MLP as the tagged model. We treat this method as the baseline. By comparing the dark bars and corresponding shallow bars, we observe that our proposed Attac consistently outperformed the baseline. Second, larger sampling ratio leads to better performance. And this is also expected as the positive sample and negative sample tends to be more similar to each other on smaller subgraphs, making the Attac model more difficult to distinguish between them. And in addition, the Attac accuracy on min pool is better than the others. We suspect this is because diff pool and min cut pool decompose the graph structure during their pooling process. So the subgraph as a whole might never be seen by the tagged model. And this makes it harder for the graph embedding matching to be effective. Okay, here is the third Attac. It's graph reconstruction Attac. The objective is that given the tagged graph embedding, reconstruct a graph that shares similar graph structure statistics with the tagged graph. And we use graph autoencoder to serve as the Attac model. Different from traditional autoencoder in image domain, the graph autoencoder here has an addition graph matching component. The reason is that there is no explicit node ordering enforced in the graph. So to guarantee that similar graph has similar adjacency metrics, the order is very important. After the autoencoder is trained, we use the decoder as our Attac model. So given the tagged graph embedding, the decoder can reconstruct the graph. And here is an experimental result. We use two types of metrics to evaluate the tag performance. The first one is graph isomorphism. It directly compares two graphs using graph kernel. The graph isomorphism of one indicates two graphs are the same. And the second metric is the macro-level graph statistics. We adopt two widely used statistics here, such as degree distribution, etc. We use cosine similarity to measure the similarity between the tagged graph and constructed graph. We show that our proposed graph reconstruction Attac achieves good performance for both metrics. And finally, we also investigate a simple defense mechanism, which is adding random Laplacian noise on the graph embedding before it is published. The x-axis here is the standard deviation of the Laplacian noise. The y-axis is the model performance. We observe that the defense can effectively mitigate the tags while maintaining acceptable accuracy drop for normal graph classification task. So to conclude, through our attacks against the graph embedding, we found that directly sharing graph embedding is not safe. And we show that perturbation-based method can mitigate the inference attack, but sometimes at the cost of model utility degradation. And in this paper, we only consider reconstruct the graph structure. One interesting future work might be reconstruct node feature as well. Besides, when an adversary can access different information, will leakage be more severe or not? It's also very interesting. And we have evaluated graph recovery attack against the node embeddings. And for more details, you can check our paper Finding Nemo. And that's it. Thanks for your listening, and now I'm happy to take any questions.